I just want to get through this part 5. I just want to get through this part. Okay, and it seems like recently I jinx myself if I say we won't be here the whole time. Anybody in here like to work on puzzles? Like jigsaw puzzles?
I like Sudoku.
No, yes. Sudoku? Okay.
I just got a big book of it this weekend.
Well, it's kind of, I don't know if this is kind of like Sudoku, but it's like a it's like not crossword puzzle, it's like a jigsaw puzzle to me. Sudoku hurts my brain. But there's a sort of problem in chemistry called Hess's Law problems. And they deal with enthalpies associated with reactions. So, for instance, we're going to have these reactions called the reaction of interest, okay? And it must be a complicated reaction of interest, for which we do not know we don't know the enthalpy of the reaction, okay? But if we know kind of, I call them baby steps, if we know kind of some simpler reactions, and we're going to talk about how do you add reactions together. We're going to get to that. Basically, I'll tell you how you add reactions together. You line them up on the reaction arrow, you add all the reactants, you add all the products, you kind of meet down at the bottom. That's how you add chemical reactions together. So in Hess's law, we say there's a reaction, an overall reaction of interest that's kind of maybe complicated. And if we can describe that overall reaction of interest into simpler reactions 1, 2, 3, 5, and add them together and make the overall reaction of interest, then we can actually get the enthalpy of that reaction of interest. So here's what it looks like. Basically, you have your RXN of interest. And on your homework hints, I notice I'm going to put a star there. And then you have 1, 2, 3. Let's just make 3 baby ones. And your up here, your enthalpy of reaction for your reaction of interest is unknown. Okay, but you know these. And like I said, where it's going to be about adding chemical reactions. If you add them together, and if this chemical reaction is equal to your if that reaction is equal to, the sum of the reactions is equal to your reaction of interest, then we can actually just add these together. And the sum of this is equal to that. That's it. That's all. Totally it. But now, does it really occur in steps 1, 2, and 3? Well, not necessarily. If we can actually, it's almost like a kind of force fit. If on paper it adds up, those little ones add up to the overall one of interest, it doesn't mean that it really has to proceed by that, what we say, mechanism, or that set of baby steps. Because we talked about state function versus path function. State function just says where you start and where you end. It doesn't matter how you got there, okay? So that's kind of nice. So the example we're going to look at is burning the hydrocarbon benzene, C6H6. We're going to combust it and combine it with oxygen, and it's going to form carbon dioxide and water. Now, when we did combustion analysis problems, we didn't worry about stoichiometric coefficients. Now we need to worry about stoichiometric coefficients. So this is actually balanced. For 1 mole of benzene, it combines with 15½ moles of oxygen to form 6 moles of CO2 and 3 moles of water. Okay, so you could put a star up there next to the top one, and these are our potential puzzle pieces. Okay, so the reaction of interest is the combustion of benzene. What do we have to work with? Well, one of the things we have to work with is simply combining carbon with hydrogen to form benzene. And there is an enthalpy associated with that. Remember, delta H is enthalpy. It's endothermic, 49 kilojoules of energy. According to that, those stoichiometric coefficients. Our second puzzle piece is this one, where we're taking carbon and combining with oxygen to form carbon dioxide. It's exothermic. So remember we talked last week that that's the amount of energy given off specific for 1 mole of carbon, 1 mole of oxygen, and 1 mole of carbon dioxide. And our last puzzle piece is this one, where we're just forming water from hydrogen and oxygen. Again, exothermic. Now, you might be wondering, well, now, Mrs. Snipes, if I do a Hess's Law problem, will you always give me the puzzle pieces that I need to solve the, and the answer is yes. I'm trying to think. Pretty much yes. So let's see how we can actually use these in the green box, 1, 2, and 3, to get the overall reaction of interest. Before we do that, I need to mention something, and it actually has to do with, when I go back to this one, notice that carbon, of all of the other reactants and products, carbon actually, it's not only a solid, but it's a solid carbon in its graphite form. That's because there are different forms of carbon. Different forms of carbon would be called allotropes of carbon. Okay, so other elements have different allotropic forms. The different allotropic forms would have different thermodynamic properties, and so that's why I mention it. And that's why when you see it in a problem, it will specify. So they're all solids, these different allotropic forms of carbon you're going to see, and I know you know these forms. But it's not just carbon that has different allotropes. Lots to write for that one. So here we go. So, and I have them on the next slide. We have carbon as a diamond ring. Carbon atoms lined up as graphite, like in your lead pencil. Isn't that weird? It's like lead pencil, but it's carbon. And then over there we have, I don't know if it's relatively new, in the 1980s maybe, they found actually carbon in this arrangement where those bonds there are a type of covalent bond, I want to say. But they found it on, it was extraterrestrial, like on a meteorite. So carbon, as it exists in your diamonds, this is kind of showing you what that looks like. I have a lot to add to these. There's carbon, little carbon atoms as a diamond. This is carbon atoms kind of in sheets of material in graphite. And this is carbon as it's arranged in a buckyball sort of allotropic form. All right, back to the problem. So that's why carbon actually has to be specified here as to which allotrope of carbon are we talking about. Carbon is graphite. Okay, so these are our babies down here, our puzzle pieces. This actually is our overall reaction of interest. That is our picture we want it to look like when we're done. So here's how it goes. You're going to see me step through each equation and compare. I'm going to start with 1, and I'm going to compare the puzzle piece with the reaction of interest. Okay, equation or reaction of interest. And I'm going to find something that matches up. So in this one, do you see if we focus on the formation of benzene, and this actually, the reaction of interest has benzene as a reactant, not a product. So we talked last week that we can swing it around the reaction arrow, but what happens to the enthalpy? Becomes negative. Yep, exactly. So we're going to swing it around. And the convention I use is, as you prepare these baby equations to be added up, I usually step it up from just equation 1 to equation 1 prime. So here's what we started with, 1, and then on my answer keys and stuff like that, 1 prime is the manipulated one, ready to go. Not only that, but usually in my answer keys, I will actually insert something right after 1 prime, and then it will say, I took 1, and I took it times minus 1. Does that make sense? I took 1, minus 1 means I switched it around. That's kind of my convention. Cool. So set that aside. We're going to come back to that one. Now let's look at the second one. Oh, by the way, yes, you said the enthalpy of this reaction, then, since we swung it around, is not going to be positive 49.0 kilojoules. It's going to be negative 49.0 kilojoules. Awesome. Okay, now let's look at the second one. This is the second one as written. Now sometimes it's easier to see than others, but the carbon doesn't match up. The oxygen matches up, but that looks potentially problematic. The CO2 is looking like a possibility here. I think that's what we look at. So we need to scale it up, don't we? So we said actually you can write 2' and scale it up like this. So here's our 2'. We scaled it up to get 6 moles of CO2 because we have 6 moles of CO2 in the reaction of interest. This is a good point, maybe to warn you that if you had CO2 in any of your other puzzle pieces, it becomes what we call confounded. It's not clear. So if you go to monkeying with this one to make it fit, you can't really do that because you have other stuff to add into it. So we picked something unique. CO2 is unique to number 2. So of course now we're going to have to multiply the heat of the reaction, the enthalpy of the reaction, heat of the reaction, it's the same thing. So delta H2' is 6 times 2. So if you take 6 times negative 393.5 kilojoules, you should get 2,361.0 kilojoules. So again, what I usually do for my prime down here, or what I would do for my prime right there, is I would say 2', and I would say I'm going to take equation 2 times 6. That's probably what I would do. And set it aside. So this is kind of nice. You probably want to have a nice big old piece of paper to do this. All right, let's look at the third one. And something that's unique, of course, is the water that's formed here. It's on the right side, so we don't need to swing it around, but we need to scale it up to 3. So multiplying by 3, don't forget you have to multiply everything by 3. So we get, instead of 1 H2, we have 3 H2. Instead of 1/2 O2, we get 3/2 O2. And now we get our 3 H2Os, which was what we're after. So we have to then scale up our heat of reaction, take it times 3 also. So if you take negative 241.8 times 3, you get negative 725.4. So far, so good. An important part to get full credit to work this, I don't know how I want to put it, they're both, you want the credit, but you also want to do it right. The next step then is to take those primes, to line them up, and add them up together. So here are our 3 primes. Manipulated, right? So what you're going to see, or if I was doing it, I guess I put it this way, I would like to line up, I would take this and scoot it over here, okay? Because I kind of like to line up all my reactants and all my products. This looks a little funky, but it just was easier to do it this way. I guess I could kind of scoot that over, anyway. So we're going to add them up, and then we're going to have reactants goes to form products down here underneath there. Now, it should add up to the reaction of interest, but let's just see. So notice one of the things, and you can simplify before or after. Right now, I'm simplifying before. Notice I have an X through the 6 carbons on the product side of the first one, and the 6 carbons on the reactant side of 2'. Okay, they cancel each other out. Now, alternatively, and you'll see me sometimes, I just bring them down and then let them cancel. So they cancel. Similarly, with our H2s, they cancel. But don't worry if you want to bring them down and then cancel them. And then with our O2s, we need to combine those 2 terms. So we have 6 moles, and we're going to add 6 moles to 3/2 moles. Of course, 6 is 12/2. So 12/2 plus 3/2 is 15/2. So that's all that can be combined, and that's all that can be canceled. So now we're ready to bring down what's left over. So what's left over on the reactant side is 1 mole of C6H6, 15/2 moles of O2, and on the product side, we have 6 moles of CO2 and 3 moles of H2O. That's how you add those 3 equations. So in order to get full credit, you need to convince me that, or yourself, that if you manipulated your baby equations, okay, that they now add up to be the equation of interest. Well, if that's the case, then we can go ahead, and it is, we can go ahead and revisit those 1', 2', and 3', the heats of reactions, and just add those together. So here we go. 1', 2', and 3'. So there's a few steps in all of this, right? So, and I'll tell you, I'll include myself in this, it's really easy to lose a negative sign. Okay, we are going to add these together. Don't lose your negative signs. So when we add all these together, and when you add them together, we don't do a lot of addition like this in chemistry. We round according to decimals. So here we go. So if you add those 3 energies together for 1', 2', and 3', remember you can show it in parentheses and put the units outside. You get you have to round to the nearest tenths, and you get negative 3,135.4 kilojoules of energy. So again, without knowing the enthalpy of the reaction of interest, the combustion of benzene, the fact that you had these other 3, you did know the enthalpies of reaction for these other 3, now you know that enthalpy. Ta-da! Is that it? Oh, sorry. Yep. Okay. See, I told you it'd be short. So take a look at these. Some people like Hess's Law, and some people think it's very annoying. So we'll see which category you fall into. While I was looking at these at my office, I'm like, are you serious, Mrs. Snipes? I don't call myself Mrs. Snipes. But I really give you a lot of hints, so you might not want all of these hints. I'm just telling you ahead of time. So the first one looks like this. Now notice when you get it out of your book, it won't have the star reaction of interest and 1 and 2. I added that because I think it makes me remember where I'm going back to. Okay, so I kind of said, because I think I like doing Hess's Law problems. If you look at 1, the problem with 1, and to get to 1' is the CO's on the wrong side, so you reverse it. Okay, and the problem with 2, if there is a problem, there isn't a problem. See, notice my little hints here? I interpret it as what I do to 2', I basically take 2 and I multiply it by 1. I leave it the same. Okay? And don't forget this step. Now you have to convince yourself that if you draw a line there and add up the reactants and the products, that they will equal the reaction of interest. To me, only then can you say that let's go ahead and add up those heats of reaction, and that will be the heat of the reaction for the reaction of interest. Okay, so that's the first one. The second one, okay, again, I added the star and the 1, 2, and 3 just because I did. Looks like the first one you multiply by 2, focusing on the hydrogen. Now, each time you look to how you want to change your given equation into a prime, you should focus on something that's unique. Don't focus on something that exists in multiple pieces, because that's like chasing although there is one where you have to do that. I'll try to make sure I catch it. Looks like the third one we just need to reverse. Well, it looks pretty good. Add equations to get the reaction of interest, and if that matches your reaction of interest, hopefully it will, then you can go ahead and add up your enthalpies. This one, reaction of interest is that thing up there at the top. Those are your puzzle pieces. Is this one? Now this is a good example. For instance, do you see water? H2O is formed in 1 and 2, right? Is there H2O in the reaction of interest? No. So actually, I think when I give you my hints, that's one of your things, is you have to annihilate the H2O as you manipulate your 1 and 2. It is kind of like Sudoku. Okay. So for the first one, my hints were to focus on, for 1', if we look at the Cl2, looks like we need 2 moles of we have 2 moles of Cl2 in the product. Looks like our reaction of interest has 1 mole of Cl2 on the reactant side, but our piece has 2 moles of Cl2 on the product side. So we're going to do 2 things with that. Looks like my key is wrong. This should be, sorry guys. We're going to reverse it, and we are going to not multiply by 2. We are going to multiply by 1/2. Final answer. Sorry. Can you read that okay? 1 times -1/2. Okay. Now, let's see what other hint I said. Oh, maybe I didn't. We don't have to worry about the water. Things kind of fall in place. So Cl2 is unique to 1, and the reactant C2H4Cl2 is unique to the second one. The problem with the second one, of course, is it's on the product side and you need it on the reactant side. Are you serious? Boy. So I need to multiply through by -1. Can't believe that. Well, I can. How come I never caught this before? Because to me, we got to reverse it. Are we good with that? Are we looking at the same thing? Look at 2. Okay, blah, 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 goes to form C2H4Cl2. Where is that in the reaction of interest? Oh, it is on the product side. Okay. Okay, I can take that one back. I was right the first time. So it's already positioned right. I was looking at the wrong thing. Any questions about that? So I take that one back, but I still
So when you
had the
put
wrong one.
negative, that means it's reversed.
When I put a negative, yeah, next to my prime number, that means I've reversed it. Yep. Yep. So the other one is -1/2, -1/2, because we have 1 mole Cl2 and 2 moles of Cl2. Yes.
And then you would make the 202 positive.
Correct. Yep. For 1', it would be positive, and you divide by 2, multiply by 1/2. Yeah.
When we set it up, is it okay if we just do 1' times 1 times a -1/2?
Yes.
Or do we have to just, okay.
Yeah. That's what yeah. And the waters, crazy as it is, you can actually just kind of see, eyeball and see what's going to happen with the waters. When you take the first one and you divide by 2, you're going to have 1 mole of water there, okay? And actually, we're going to reverse it. So actually, 1 mole of water is going to be over here. So we're going to have 1 mole of water over here. And for 2, we're going to have 1 mole of water over there. So those are going to cancel each other out. So we didn't have to worry about the water this time. But prove that. And I think what I've gone to on your exam, so you'll have a Hess's Law problem on your test. You put test on here, you can, but it's like obvious, things that we do in lecture you're going to see on your test. And what I've done to basically is I draw a line and I say do your work down here. Because what I had students doing is basically sticking in coefficients and numbers and drawing up there on my typed stuff. So you have to rewrite your stuff underneath it. Okay. So we're just kind of getting that habit. Okay, yep, add equations and then add the enthalpies of reaction. One more. Maybe this is the one, we'll see. We have 3 puzzle pieces to deal with and 1 reaction of interest. Make sure I got these right. What I said was for the first puzzle piece, if you focus on that focus on the N2, it's in green up there. We want to form 1 mole of N2 in a reaction of interest. We have 1 mole of N2 formed in that one. So look, don't do anything with it. And you don't have to use my hints if you want to kind of find your way through them. That's great too. For 2, I said I would look that up. Yeah. So for 2, I would focus on the water. I knew there was water in there somewhere. But know that you get water from 1 also. Now by that time you had visited 1 and you said, I'm going to leave 1 alone. If you do that, 1's going to give you 2 moles of H2O. So in your second, in your 2', you somehow got to get 2 more moles of H2O. So that's why I said multiply through by 2. So you get 2 moles of H2O here, 2 moles of H2O over there, and you need 4 moles in your reaction of interest. So that's how that would be. So and then for the last one, that does have something unique for the 3. Notice that 3 was the only place where you had the hydrogen peroxide, the H2O2. Nobody else has H2O2, and it does appear in the reaction of interest. Notice in the reaction of interest, it's on the reactant side, not the product side, so you're going to have to reverse it. And notice you need 2 moles, not just 1. So reverse it times 2. Then it's kind of like almost a Hail Mary. So once you have them manipulated like that, you have your 3', you're like, oh yeah. And sometimes I've gone to grading tests before, and you know, we make mistakes. I make mistakes when I work chemistry problems too. And it'd be like, they don't add up right, you know. I'm smiling, but it's not really funny. The test is hard because it's a, but my point is, go ahead and add them together anyway. Don't just, and be honest if it doesn't add up. So these should, if you follow my hints, work out. Okay, so that was it. I'll push those out there. Again, you don't have to use them, you can use them, but you will have one on your test a week from Thursday. Okay? That's all I got.
What was the date of the test you want to start?
20th, I want to say. Is that a Thursday?